Okay, so in the last section, we talked about compound interest, both at specific times and continuously. Those are both examples of exponential growth. If you look back at the compounded semi-annually, blah, 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 and that stuff, you'll see that it's actually in the same format as an exponential growth formula. Now this one, the half-life or radioactive decay, basically what it refers to, is given by this formula right here. So half-life is when you take a mass of some kind of radioactive substance and eventually it starts to decay, right? One of the things scientists looks like is the half-life, how long it takes until it gets to half of its original amount. So the formula looks like this. A is the initial mass, H is the half-life, and it's got a very specific formula, or sorry, it's important for a specific part, the R. And then the remaining, mass remaining, that's this M right here. At time t is modeled in the function right there. Notice it's a negative on the R because it's decaying. Now this is what I was talking about with half-life. This R right here is the ln of 2, always 2, right? Divided by h, whatever it tells you is the half-life of it. So this problem says the half-life of blah, blah, blah is 1600 years, okay? Half-life is h, 1600. Suppose we have a 22 milligram sample. That's the amount you started with, which is going to be A. Find a function that models the mass remaining after t years. So our mass after t years equals, I've got my A, 22, that's times e to the negative. Now I don't have r because I've got to calculate r. Right? R is going to equal the ln. See, it was doing so good. R equals ln of 2 divided by h, which was 1600, which is about 0.00043. Now in the calculator, and if I had a picture to show it to you, really, I would. Let's look at it on Desmos just so you can see what it looks like. Okay, if I type in here, let's go ln, parentheses, 2, whoops, that's not 2, parentheses, got to get out of them, divided by 1600. That's what you get. On the calculator, it gives it to you in scientific notation. It has the little e at the end, so be careful. Just know that e means to move left, whatever the number is. For example, let me write this down so you guys can understand. This is what the calculator gave me. It said 4.332, blah, 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 blah. And then at the end, it had this capital E and a negative 4. This says, move the decimal left, 4, because this is a 4. So I went 1, 2, 3, 4. That means I had to add 3 zeros, and that's where I got 0.00043. Desmos will give you the zeros inside there. Okay, finishing out our formula, that means right here is going to be 0.00043, and then a t on the end. So final formula, m of t equals 22 e to the negative 0.00043 t. How much of the sample will remain after 4,000 years? Okay, that's a t. So we just have to plug it in. The remaining mass, 22 e to the negative 0.00043 times 4,000 is about, looks like I get 3.94 And then we're talking about mass, and it was given to us in milligrams. So half-life radioactive decay. This is a huge application of exponential decay. Sorry, words aren't coming. All right, let's look at this one. Polonium-210 has a half-life, okay, keyword there, of 140 days. Suppose a sample of the substance has a mass of 300 milligrams. That's our starting value. So this right here is our H. This right here is our A. Find a function that models the amount of the sample remaining at time t. Okay, just like before, we've got m of t, or y equals, doesn't matter, 300 e to the negative, I need to find r first. So let's go over here to the side and find r. R equals, I don't get it. Quit. R equals ln of 2 divided by h, which was 140. Okay, that's about, just going to go down here and change this to 140. 0.00495, so that would technically round to 0.005. So we're going to use 0.005. Okay, 0.0. Why is it doing that to me? I just don't understand. Like, I'm at a loss. I don't know what's happening. All right. Point. Ugh. Sorry, that was probably loud in your ear. 0.005 T. Just write really slow. Find the mass remaining after 1 year. That's a time. T equals 1. So our mass is going to be 300 e to the negative 0.005 times 1, which is about, looks like about 298.5 milligrams. Next question says, how long, that's a T, will it take for the sample to decay to a mass of 200 milligrams? So this is our M. Same A, same R, but now we're given the M, and we're going to have to solve for T. Okay, solving just like normal, just like we did on the exponential ones the other day. Got to get rid of that 300. Technically, that's 2,000, or sorry, 2/3. I don't know what that has to do with 2,000. Equals e to the negative 0.005 t. Okay, got to write it with my exponent on the left. Equals 2/3. All right, e automatically turns into ln. Okay, switch sides. 2/3 equals negative 0.005 t. Last step is divide by negative 0.005. Negative 0.005. And then t is approximately, let's go to Desmos. This time it's, we'll start over. We've got ln of 2/3. So I'm going to type in ln parentheses so that it knows I'm talking about the function. Oops, I didn't want a capital L. Now it knows. 2/3, so 2 divided by 3, and then get outside the parentheses. Then you're going to hit the divide by negative 0.005. looks like it's 81.09, blah, blah, blah. We'll call that 81, which is about 81 years. So after 1 year, it decreased to 298. And after 81 years, it will get down to 200. Seems about right. Okay, exponential growth and decay. One of the biggest applications of growth is the compound interest. A big example of exponential decay is this half-life idea. Now the formula has an E in it. That's just that whole continuous thing. So if you want to talk about regular decay depreciation, that would be an example of like this. Simple ones where the car depreciates or something decreases. But when you're talking about radioactive decay, it's talking about a continuous thing, which is where E comes in. Anyways, that's it.